Hi everybody! Today I want to experiment a little bit with virtual reality. However, I don't have a VR headset at hand. But luckily, I don't need one. Because you can actually create immersive experiences with just a regular computer screen. Because if you know the position of the viewer, you can actually adjust the rendering so that objects may appear behind or in front of the screen. But let's start in the beginning. How can you actually determine the position of an object in 3D space? There are quite a few methods, but one of them is using such a marker and a regular camera or webcam. This is an Aruco marker I had lying around because we are using them in a former project, and their main purpose is to be easily locatable by computer vision systems. I wrote a small test program to test the marker detection and pose estimation. The program adds a rectangle to each detected marker as well as the corresponding ID. The estimated position and orientation relative to the camera is printed to the console. As you can see, the detection of the marker works quite well, even when I hold it at a really steep angle. However, the marker I had lying around was really big, so I printed out some smaller ones. 3 by 3 centimeters work really well. However, 1 by 1 centimeter was a little too ambitious, as the marker didn't get detected very well when being a little too far away. Detecting the markers using OpenCV was really straightforward. It basically boils down to 4 function calls. Reading the image from the camera and converting it to grayscale, then finding the corners of all markers in it, and finally using the position of the corners together with some camera parameters to estimate the pose of the marker. I didn't even bother to measure the actual parameters of my camera using such a fancy calibration board, as the results were good enough using the parameters from another camera I found online. So for now, let's assume we can track the position of a potential viewer. But how do we take it into account during rendering? Imagine we have a screen with a certain width and height, as well as a viewer standing in front of that screen. When we shoot rays from the viewer's eye through each of the 4 corners of the screen and connect the rays, we get the view volume that is covered by the screen. As you can see, the view volume changes when the viewer moves, so we need the position of the viewer's eye. For that, let's introduce a coordinate system with the origin at the center of the screen, where the x-axis points to the right, the y-axis points up, and the z-axis points towards the screen, so that everything in front of the screen has negative z values and everything behind the screen has positive z values. Now, we can express the viewer's eye position in this coordinate system using the values ex, ey, and ez. Note that using this convention, the value of ez is always negative. Let's visualize the view volume again and look at everything from the top. In order to make the view volume a proper frustum, we need to define a nearplane. The nearplane is perpendicular to the z-axis and is located a distance of zn from the viewer's eye. It specifies the minimum distance at which objects are visible. Although technically not necessary, we also define the far plane at a distance of zf from the viewer's eye. Similar to the nearplane, the far plane specifies the maximum distance at which objects are visible. Now, the goal is to find the matrix M that transforms this frustum into a half cube, where the x and y values range from -1 to 1 and the z values range from 0 to 1. We will now construct the matrix M step by step by combining several transformations. You can see the current state of the matrix M in the lower left corner. First, we will make the frustum symmetric. When we draw a line from the viewer's eye to the center of the screen, it will perfectly cut the view volume in half along the z-axis, indicating that the x and y coordinates are skewed by a factor of z. To determine this factor, we divide the offset in x and y for a given z. To reverse this operation, we need to negate the factor. This factor can now be used to construct a shearing matrix hxy that will make the frustum symmetric. I use this arrow notation to show what the matrix does to a point in 3D space. Here we can see that after applying the matrix, the x and y coordinates are skewed by our previously calculated factor of z, while the z coordinate remains unchanged. Now let's see what happens when we apply this matrix to the frustum. Perfect! The frustum is now symmetric and the viewer's eye now also lies on the z-axis. However, we actually need to move the projection point into the origin of the coordinate system. This can be achieved by translating everything by Ez along the z-axis, which is done by the translation matrix Tz. Now that the frustum is symmetric and the projection point is at the origin, we could simply apply a standard projection matrix as found in most computer graphics math libraries. However, for the sake of completeness, I will also explain how we can derive the rest of the matrix. The next step would be to apply a standard projection matrix, which basically divides everything by z. However, if we apply the projection matrix now, we notice that the frustum does not span the range of -1 to 1 in the x and y direction. We could apply a scaling matrix now, but I think it's easier to reason about the scaling factors before the projection. So let's reverse it. See, we want that all points on the edges of the frustum map to -1 or 1 respectively. However, because the projection matrix divides the x and y coordinates by z, this is only the case when the x and y coordinates are equal to z or negative z. In other words, we need to scale the x and y so that the opening angle of the frustum is 90 degrees. To get the scaling factor that achieves this, we divide the z coordinate of any point on the edge of the frustum by the corresponding x or y coordinate. These factors can then be used to create the scaling matrix Sxy, which scales the frustum so that it has an opening angle of 90 degrees. When we apply the projection matrix P now, we can see that the frustum now correctly spans the range from -1 to 1 in x and y direction. So, the x and y coordinates are now correct. However, we still need to ensure the near plane maps to z equals 0. This can be done by applying the transformation of the current matrix to the near plane, which is located at Ez plus Zn. Plugging this value into the formula for the transformed z coordinate shows us that the near plane is currently mapped to z equals -1 over Zn. To correct this, we need to translate the z coordinates by 1 over Zn using the matrix Tz prime. While it may look like we are done, if we look closely, we can see that the far plane is not correctly mapped to z equals 1. We can use the same trick from before to fix this. We look at the transformation of the current matrix, plug in the far plane, which is located at Ez plus Zf, and construct a scaling matrix Sz, which scales the z-axis according to the inverse of the computed value. And that's it. We have successfully constructed the matrix M that transforms the view frustum into a half cube. Okay, now we have a way to track a viewer's position as well as the knowledge to correctly take it into account during rendering. With that, I built an application that utilizes both using my visualization framework Ovis. First, I created a scene component struct called marker detector, which has two methods: a constructor and a method that returns a transformation matrix from the camera to each detected marker in the current frame. This is basically the same code as in the test program earlier. Then, I added a scene component which actually stores the detected markers and their transforms. To update this component, I use the corresponding method of the marker detector in a system which gets called every frame. Then, I added a viewport component called Egocentric Projection, which stores the relevant information to create the projection matrix. First, we need the ID of the marker that should be used to track the viewer. However, when attaching the marker to a viewer, in this case my phone, there might be an offset between the origin of the marker and the viewer's eye, in this case my phone's camera. This offset is represented by this vector. Next, we have a transformation matrix that describes the camera position and orientation relative to the center of the screen. All these attributes are necessary to get the position of the eye in the correct coordinate system. Now we need the remaining parameters for the egocentric projection matrix, namely the size of the display and the distance of the near and far plane. This system finally creates a projection or view-to-clip matrix based on the egocentric projection parameters and detected markers. First, it looks up the marker transformation and transforms the eye position to the proper coordinate system. Then, it creates a matrix that should look very familiar to you if you've paid attention during the last part of the video. This matrix is then written to the view to clip component. Because the system depends on the detected marker, it is updated whenever any marker moves. Finally, I have a system that sets everything up in the beginning. First, I initialize the marker detector using the built-in webcam of my MacBook. Then, I initialize the Egocentric Projection parameters. I chose marker 18 for no particular reason. Then, I carefully measured the offset of the marker origin to the phone camera, which was about 2 centimeters. Equally carefully, I measured the dimensions of the screen, which are roughly 30 by 19 centimeters. To transform from a camera to the display space, I need to negate all 3 axes and offset it by half of the screen's height, as the camera sits on top of the screen. For the near and far plane, I chose a distance of 1 centimeter and 10 meters respectively. Finally, I added a red cube with side length of 10 centimeters to the origin of the scene and added some lighting. And that's everything. Let's have a look. When starting the application, nothing is visible. This is because the marker has not been detected yet, so the projection matrix has not been written to. However, as soon as the marker is visible from the webcam, we can see the cube. When looking straight at the output from the display, the cube looks really distorted. However, from the point of view of my phone, the cube looks fine, and it actually looks like it is partly sticking out of the monitor. The effect becomes even more pronounced when I reduce the size of the cube to 5 centimeters and move it 10 centimeters in front of the screen. Now, it kinda looks like the cube is hovering above the keyboard, which I think looks really cool. The tracking is not perfect, as you can see a little bit of stuttering here and there, but I think overall it's pretty usable. And obviously, the illusion breaks down when parts of the cube are no longer visible anymore, or when there's too much reflection on the screen. However, when the conditions are ideal, it looks pretty good. And I think it's a really cool trick, because remember, the actual output of the screen looks something like this. Only the right perspective makes it work. So, this worked quite well for my phone with a marker attached to it. However, what to do if Phanti or I want to have that experience? Of course, we could also glue a marker to our head or get a really nice face tattoo. But I believe there's a better way. However, this video is long enough already, so I'll leave that for a part 2. If you want to know what I have in mind, you can subscribe to my channel so you don't miss it. But for now, thanks for watching.